Welcome back. We are going to be talking about friction today, and you will see that there's still overlap between Newton's first law and Newton's second law with friction. Just a little heads up, if you see these little arrows here, we're going to be talking about free body diagrams in them soon enough. So that is a little bit of something we'll tiptoe in today as well, but we'll get on to it full force here in a couple days. First of all, to define friction, let's take a look at this picture down here in the bottom right corner. It's a microscopic view of the surfaces between this box and this cement block. Notice that there are inconsistencies and irregularities between the two surfaces. Even though they may have been sanded down and feel smooth to our hand, there's always some type of irregularities that, had trouble saying that word. There's always some type of irregularities, though, between them, for sure. In order to measure the force of friction, it depends on two things. First of all, it depends on the type of material that comes in contact. So, are you touching sandpaper or glass or ice? And then also something called the normal support force, which we've talked about a little bit, but we'll go more in depth next. The normal or support force is basically the surface pushing back up on an object. So in this first example here, we see a book sitting on a table. Obviously the table, because of the force of gravity, has weight to it, but because it's not moving, it is equal to the normal or support force that the table is pushing back up on the book. And that's what support force or normal force is. It's just the surface pushing back up. If we want to be a little more specific, the weight of this object, 20 kilograms, is about 200 newtons for the weight, and that's pushing down, we see. But that means then that the normal or support force pushing back up is equal to 200 newtons, just in the opposite direction. If an object is not moving up or down, we often can assume then that the force of gravity or the weight of an object is going to be equal to the normal force. So that's an assumption that we can make. If I wanted to calculate the force of friction, which is just mu times the normal force, let's take a look at it. First of all, and I apologize, but this should be more of a lower end. So it should be force of friction is equal to mu times the normal force. But let's look forward into it. The force of friction, since it's a force, it's going to be measured in newtons. Mu, which is this Greek symbol right here, is considered the coefficient of friction. What that is a number that basically rates how much friction is found on the surface. It doesn't have any units, and the number is usually less than 1. It's usually between 0 and 1, somewhere in there. But that number is going to tell you how much friction is involved. And then, of course, the normal force, which should be F sub n. Sorry about that. But the normal or support force is measured in newtons, and as we just learned, it's that force pushing back up on an object to keep it on the table or keep it on the floor. Tidbits of information about friction. First of all, friction is always opposing the object's motion. So if this guy is pushing the box this way, then our force of friction would be the exact opposite direction. If something is being pushed up the wall, force of friction is down the wall. If something's being pushed north, force of friction is south. So we can represent the force of friction with an arrow because it is a vector quantity. But also, something must overcome friction in order for the object to move, whether that's an applied force, which we would say is Fa, or a force of tension like a rope, which we'd say is Ft, or the force of gravity, which is Fg. One of those things or other forces have to overcome friction in order for it to move. When we do apply a force, a push or pull, and it ends up equaling friction, that either means that the object will not move or it will move at a constant velocity. The reason for that is that the object will be in equilibrium, so all the forces are balanced out. And if that's the case, if the forces are balanced out, then inertia takes over. If the object wasn't moving and forces are balanced out, the object will continue not to move. If the object was moving and all forces are balanced out, then the object will continue to move at a constant velocity. This silly cartoon over here says, hey, if I push my lawnmower just enough to cancel out frictional force, then you will mow the lawn at constant velocity. That's pretty sad if a couple is talking about that at their house, but nonetheless, that might be something I would bring up to my wife and she wouldn't be very interested in. We talked yesterday about a car using cruise control. What really is that? That's just the engine of the car overcoming the force of friction and the air resistance as well, so that it can move at a constant velocity. So you're giving it just enough force to put the car in equilibrium to move forward. Now, if that applied force is not equal but is actually greater than the force of the friction, you will then accelerate. Why? Well, because of Newton's second law, if we have F net, overall net force, then we are going to have acceleration due to this equation, F net equals ma. So if you look at this first box here, the forces cancel out, so this box isn't going to move. Look at the second equation, the forces on the x and the y cancel out, so again, the box won't move. This third equation, though, because of Newton's second law, there is an overall net force because the applied force is greater than the force of friction. Therefore, this object is going to move, and more specifically, it's going to accelerate. There are two types of friction that I want to talk about before we end our discussion. Static friction is the friction that is felt between two objects that are not moving past each other. Think about your butt in the seat of a chair. You aren't moving, but you aren't sliding out either, so there's friction between your pants and the chair. Now, if we look at kinetic friction, that is two objects that are moving past each other. And sorry, the picture kind of went over it. But that's two objects that move past each other and have friction. That's called kinetic friction. And we see that a lot, like pushing a box up here or whatever. If something's moving, the two objects are interacting as they move. That's kinetic friction. If we graph force versus time and start looking at friction, we see that there's a relationship here of static friction and sliding or kinetic friction. Sliding friction and kinetic friction are the same thing in this case. Just so you know, two terms for the same thing. Static friction always takes a little bit more force to overcome. And then once you're sliding and moving, your kinetic friction is a little less force. Why is that? Well, an object not moving has inertia, so you have to overcome that and get the object to move. Plus, you have to overcome friction and push it slightly harder to get it to move. Now, once it starts moving, as you can see, the object already has inertia in motion, so you can just continue pushing and canceling out that friction in order for it to keep sliding. So kinetic friction is always a little easier and a little lower. But if you're pushing harder, eventually you overcome friction and inertia and it starts moving, it drops down and goes forward. We will do a lab that will look very similar to this, where we will push, overcome it, start moving, and then that force will drop down so we can keep moving at a constant velocity. All right, let's end with an example problem. We have a 56 kilogram object, which is our mass, slides across the floor and has a coefficient of friction that is equal to 0.45. And we want to know what the force of friction is overall. So the force of friction overall can be calculated by taking the force of friction equal to the coefficient of friction times the normal or support force. If I want to plug in for that and find my force of friction, I can just use my coefficient, which is 0.45, but I don't have my normal force yet. Though I've been given the mass, I don't have the normal force. What I can do is a side calculation and figure out the weight of the object, because the weight of the object will really be the force of gravity, and the force of gravity, because the object isn't moving up or down, will be the normal or support force. So if I plug that in really quick, 56 kilograms times the acceleration of gravity, I'm going to get, the weight ends up being 548.8 newtons, which really is equal to the normal support force. And I'll tell you why. If the force of gravity is downwards, then the normal force is pushing up from the table or the floor, whatever it is. Since they're not moving up or down, they can be considered equal. And the force of gravity really is the same as weight. So that means that I can plug in now my 548.8 newtons to solve for my force of friction, which is really just 0.45 times 548.8. That ends up giving me, and forgive me for the cluttered work, a force of friction of 246.9 newtons. And all that did for me was figure out the force of friction, which is opposing motion. So if the object is moving to the right, force of friction will be to the left. And in this case, force of friction will be 246.9 newtons. Now to look into theory real quick, if I needed to keep this box moving at a constant velocity, what force would I have to apply in order to keep it moving at constant velocity? The answer would be 246.9 newtons in the opposite direction of friction. As long as you cancel out friction and move with an equilibrium, we know that inertia will take over and the object will continue with a constant velocity. That concludes our friction lecture. Thanks for listening. If you have any questions, don't forget to sign up during second hour. We'll be happy to help. Have a good day.